That's slightly bigger.
Yeah.
Okay, let's go with that. So this is joint work with Nicola Olivetti from Marseille and Claudia Nalon from Amsterdam. And in fact, it's the continuation of an earlier paper. And it's about non-monotone modal logics. And we have a standard modal language. And we have, so with the base language is classical, so we have chosen to just have disjunctions, negations, and a single box. So box is a unary operator. We just use a unary operator because otherwise we get into notational hell, but everything that I'm saying can be generalized to standard n-ary operators. And because we are interested in non-monotone modal logics, we can't interpret them in terms of cryptiframes. So what we need are neighborhood models where we have valuation in the standard sense, but also to every point W, we associate a collection of sets, and double power sets are quite often somewhat hard to get your head around to. So I will call these a collection of neighborhoods. So this sounds like topological spaces, but at the moment, we're not requiring that a world is actually an element of all its neighborhoods. But it's slightly less confusing compared to saying subsets of whatever. And the interpretation of the propositional connectives is standard. And we say that box phi holds at a world if and only if the truth set of phi is one of the neighborhoods. And one thing that I want to convince you of is that this is indeed the semantics for a very minimal modal logic. And on the left, on the left, you see one kind of semantic rule. If the truth set of phi and psi coincide, so the interpretation of box is purely in terms of truth sets, then necessarily, if the truth set of phi is a neighborhood of a world, then the truth set of psi will also be a neighborhood of the same world. And this means that we have a congruence rule for box. And this is the logical way of saying congruence. And I will call this rule RCE, rule for congruence in the modal logic E. So the modal logic E is the modal logic that you get if you just have this rule. And we can also think about this logic in terms of its algebraic semantics, which is particularly easy. And the reason is that the power set operation is self-adjoint, which means that we can trade our neighborhood function for a function that directly operates on the power set by just kind of flipping sides. And what the function if, sort of the cousin of the neighborhood function gives us, is a mapping that takes the putative truth set of a formula and maps it to the truth set of box applied to this formula. And when we do it in this way, it's very clear that there are no laws that connect if and the subset relations. So we can do quite weird things. We can say that, okay, let's define such a function on the power set of the natural numbers. And I can say that you give me a power set, I will map it to the set of all natural numbers for which we have more even than odd numbers in the given set. Okay, of course, in does not occur here on the right. So there's no implied monotonicity, there's nothing, right? So it's either everything or nothing, and it's certainly non-monotonic. And what I want to look at are calculi for logics of this kind, and specifically uniform principles for defining these calculi. And the first paper to look at is one by David Lewis, and I think that is 1974, where we find a completeness proof for all non-iterative modal logics with respect to neighborhood semantics. So non-iterative here means that the axiomatization of the logic doesn't have nested modalities. So, for example, box P implies P is okay. Box P and Q implies box, I don't know, P or Q or P would also be okay. So no nesting of modalities, but something like box P implies box P would not be okay because here we have a nested box. And so once we leave the setting of non-iterative axioms, we don't have a uniform treatment for completeness or complexity or anything anymore. And of course, there are authors that looked at completeness for a number of systems. Also, there is work on sequent calculi, so both labeled and non-labeled, but again, this is a matter of taking a particular system and coming up with a sequent calculus and then proving calculus elimination and then analyzing this. And we did the same for a number of calculi. And the observation that we had at the time was that essentially all the calculi we had were axiomatized by non-iterative axioms. Maybe we can generalize this and get calculi that uniformly cover the set of all logics that are axiomatized with axioms of modal depth less than or equal to 1. Okay, and we're doing resolution. So I'm going to give you model resolution 101. So here is the resolution rule for propositional logic. So D is a clause, L is a literal. So what we take here as a literal are possibly negated propositions, possibly negated boxed propositions. And a clause is a disjunction of literals. But of course, this means that we cannot apply resolution in any way to formulae itself. What we need to do first is translate formulae to a clausal form. So in order to do this, it turns out that we need to speak about global validity. So if we think about, for example, what we need to do if we want to translate the formula box phi to something that looks like a clause, So what we're going to do is we're going to create or to generate a new propositional variable P. And we're going to replace the formula box phi by box P. And then we need to ensure that P and phi have the same truth set. So what I want is a formula that expresses that P is equivalent to phi, not at a particular point in the model, but at all points in the model. So this should be something that's globally true. So we're going to use a global modality. And you've seen formulae before. So I also need to talk about the syntax. And this is either a formula in the standard way or a formula prefixed by the global modality. And using the global modality, I can now transform formulae into sets of clauses. And I start as indicated. So I start with a formula phi. I generate a new propositional variable P. And I'm saying that P and phi should be equivalent. And then globally, the truth set of P and phi should be the same. And the transformation is then defined by induction on phi. So here's the case for the box modality. So here are two clauses that say that P and box Q are equivalent. And here's the recursive case for Q should be the truth value of phi. And doing this with propositional connectives is even easier. And now let's think about how we can set up a resolution calculus. And the observation is that essentially, at least if we think in terms of a minimal modal logic, we can think of box P or not box Q as very, very similar to being propositional literals. So there's no rules that they need to obey. And box P and not box Q will be contradictory if P and Q have the same truth set. So this is a putative resolution rule that we could come up with if we have bought the fact that we kind of need to deal with a global modality anyway. So it's not dirty or anything like that to have the global modality. And one thing that I want to notice at this point is that the statement that P and Q have the same truth value, this is possibly a statement that we need to arrive at by reasoning with the global modality. So this might not be an identity or a formula that is given, but we might need to deduce that. So that means we might need some global reasoning to actually establish this premise. So what I want to contrast this with is a sequent calculus, and we'll see more about sequent calculi. So what else do we know, or what do we know if P and Q have the same truth value? So we can think about our rule of replacement of equivalence. And this says that in this case, box P and box Q must have the same truth value. So here, this is just formalized as a single implication. Box P implies box Q. Swapping P and Q, I get equivalence. And if I had this rule, if I had the sequent calculus style rule, then I could, of course, simulate the rule above. Because if I had this, if I have, say, this premise, let's start with that premise, and I have box P or not box Q, then I can do one. Is this the wrong way around? Let's swap this and let's have not box P or box Q. And let's make this Q equals P. So what I can do is I can use this to resolve against that, and then I get D or box Q, and here I have E or not box Q, and then I could resolve the literal box Q, and I get the same conclusion. So at this moment, the only thing I want to say is that maybe thinking about the sequent calculus to generate or describe resolution rules could be a valid step forward. And this is indeed what I'm going to do. I want to sketch a procedure to obtain not only resolution calculi, but in fact, complete resolution calculi for logics with non-iterative axioms. And the first step is to stand on the shoulders of giants and cite the paper by David Lewis, which gives completeness for all logics axiomatized by non-iterative axioms over the class of neighborhood models that they define. So non-iterative just means that the modal depth is less than or equal to 1. And I gave you a couple of examples already. And the main theorem in David Lewis' paper is completeness. And I want to be slightly more precise. So there's a calculus that has all propositional tautologies, the substitution instances of all propositional tautologies, modus ponens, replacement of equivalence, which we've also seen as an axiom, and all substitution instances of our set X, which are non-iterative axioms. So there's no work here at all. There is just an observation, namely that the proof technique doesn't break if we add the global modality. And so I'm not adding the global modality to the syntax of the language. What I want to do is I want to axiomatize the notion of local consequence where psi is either a formula or a global formula, and phi, capital Phi here, is a set of formulae that may also be prefixed with the global modality or not. And this gives a very simple extension to the calculus. If something is global, then it is also local. This is this rule here. If we have a substitution instance of an axiom, then this is globally valid. And if we have one of our assumptions, I'm thinking of capital Phi as additional basic axioms, then this is of course valid, and then we add propositional tautologies, modus ponens, and replacement of equivalence. Okay, now I want to do step 2, and step 2 is in fact surprising, or I found step 2 surprising because what we're going to do is we're going to prove completeness of a resolution calculus by means of a detour through a sequent calculus. And more specifically, what we're going to do for the sequent calculus is actually to establish cut elimination. And in order to speak about sequent calculi, I'm no longer going to speak about axioms. I'm going to speak about rules, non-iterative rules. And a rule is non-iterative if the premise is just purely propositional. So the premise is here is purely propositional. And the conclusion is a propositional formula over atoms of the form P or box P. So in particular, in contrast to non-iterative axioms, there's no other connectives, propositional or not, allowed under a box. So if phi is not a variable, it is forbidden. But on the other hand, we have rules. So that means we have a premise. And it's quite easy to show that these two notions are equivalent and they're kind of interderivable. So if we have non-iterative axioms, then we have something like box phi as a subformula of this axiom. For a non-iterative rule, box phi is not allowed. So we're replacing this with box P for a new variable and add a premise that P and phi should better be equivalent. And if we have a rule under the assumption that the premise is, which is a propositional formula, is actually satisfiable, we know that it will have a most general unifier sigma, and then we stick the most general unifier into the conclusion to get an axiom. Okay, so this is my way of going from non-iterative axioms to rules. And if I want to use the David Lewis completeness later, there's also a need to go back. And what I'm going to set up now is a one-sided sequent calculus, which axiomatizes, again, local consequences. And the rules of this calculus are just sort of the standard propositional rules of a sequent calculus. And if you want to be very precise, I'm going to use the G3C sequent calculus from the book of Schulstra and Schwichtenberg. So the interesting thing is that I'm going to assume that our non-iterative rules are now given by clauses, which means that in the premise, I do something like conjunctive normal form, and then everything that's left is a clause. And I can express this as sort of standard one-sided sequence where the comma stands for or in a standard way by just replacing every disjunction with a comma. And this is so simple that I don't even want to make this explicit anymore. And given that we have the cut rule, the completeness proof is rather routine. So nothing much is happening there. We can generate propositional tautologies. We have cut. We can simulate substitution in the sequent calculus, etc., etc., etc. So there's nothing, it's work that needs done, that needs doing, but there's no real insights there. Okay, now I want to prove cut elimination. And for this to work, I'm going to make one additional assumption. And the assumption is that our modal rules are closed under cut. And the way to think about this is if we have two rules, so here's our first rule, here's our second rule, and what these rules allow us to do is they allow us to have a cut on A, right, in the conclusion. So if we do this cut, we're left with gamma naught, delta naught as a conclusion. And if we're in a situation to have a cut on two rule conclusions, what I want to find is a new rule which has precisely that conclusion that we get by applying the cut, but a different set of premises, so that these premises are derivable from the old premises using cut. So the reason why this is formulated the way it is because it's usually not good enough to take as premises all the gamma i's and the delta i's. Gamma naught, delta naught. Because what happens when you do a cut is you typically lose a propositional variable, then you lose the subformula property. So we need to change those premises in general to make sure that the lost variable is accounted for. Okay, and if we do this, we can prove a theorem about the sequent calculus. So here we've got things on the left of the turnstile, but these things on the left of the turnstile are nothing but additional axiomatic sequence. So if we could derive gamma with cut, then all cuts can be eliminated with the exception of those cuts on subformulae of our new axiomatic sequence, elements of capital phi on the left of the turnstile. And the reason for that is very simple. We do a standard Gensen-style cut elimination proof, and then all the cuts will be propagated upwards, and they will fall off the leaves. And the only problem case that we cannot deal with, if it is a cut on the subformula of kind of a new axiomatic sequence, because we can't eliminate it, we can't replace this with a new axiom just because it isn't. So this cut will remain, but that's good enough. So that means we have completeness, and the only cuts that are required are cuts on subformulae of initial sequence. Okay, and now I'm going to turn this into a proof of completeness for resolution, right? And this is the thing that I found fascinating, that you can do this. So we have a set of non-iterative axioms. I transform this into a set of cut-closed rules. And cut closure is a mechanical process. I can't necessarily compute it, but I can show that such a set always exists. And then I have a resolution calculus. This is the resolution rule that we've seen before, that we all know and love. This is the same rule under a global modality, because we need global assumptions to possibly satisfy needed global premises. This is just an imported sequent calculus rule, an element of our cut-closed rules. The last rule just says that if something is valid globally, it's also valid locally. Okay. Now let's start with a set phi. These can be local or global clauses that is inconsistent. Because of the completeness of the sequent calculus, we have a sequent calculus proof of falsity. And now let's look at this proof, right? So our new axiomatic sequence are just propositions, negated propositions, boxed propositions, or negated boxes, right? So this means that there will be no cut on any propositional formula, right? So that means cut is not going to remove any propositional formulae, which means that if we see a propositional connective being generated in the sequent calculus proof, then this will stay, because cut will not remove it, because we only have cuts on these things, which means that no propositional rules will be used, which means that the only rules that are going to be used is cut, local and global, the sequent calculus rule, and this propagation rule. Which means that our sequent calculus proof essentially proceeds by using cut or permitted cuts and the modal rules only. So that means we have a valid resolution proof. And you might argue that this is possibly not in the spirit of resolution. In particular, it's very different to the rule that I showed you earlier. This is the rule that I showed you earlier. If you follow that approach, we're not going to get this rule. We're going to get a rule that says if P is equivalent to Q, then box P will be equivalent to box Q, that we can use to derive the rule on the left, but it's not the same rule. And if you think about what we understand as being resolution, then there's an element of eliminating literals. So the cut rule eliminates literals. So whereas what we've done so far is we've generated literals, and these can then be used to get new cuts. So this is the notion, this is how we translate it from sequent calculus rules to resolution rules that generate new clauses. And we have a completeness proof for that. And the work in progress, which is happening here, is to actually translate those rules into a different format and then being able to translate the proofs. So in a similar way in which the rule here on the left simulates or can simulate the rule on the right, we also want to show that the kind of more resolution type rule can simulate the other. And this is a task of translating two different styles of resolution proofs, which we're in the process of working out, which is a bit hairy. And that's all I have to say. Thanks very much for your attention.
Thank you so much, Dirk. Any questions, remarks, comments?